In section 4.2, we're probably getting into the most important topic here in the trigonometry portion of pre-calculus with the unit circle. Now, the things that we're going to be talking about within this section, as far as what we need to make sure we understand by the end of it, our learning objectives, we'll be able to use a unit circle to define trigonometric functions of real numbers. Recognize the domain and range of sine and cosine. Sine's just the y component on the unit circle, and cosine's just the x component on the unit circle. So they both have a domain and range. They both have a range of -1 to 1. They're going to have an infinite domain, and we'll talk about why. Find the exact values of trigonometric functions at pi/4, or really any of our common angles. We'll look at that. Use even and odd trigonometric functions. So we'll be able to, like for example, if we know the cosine and sine at pi/4, well, what's the cosine and sine at -pi/4? Knowing which one is even and which one is odd gives us the answer to that. Recognizing and using fundamental identities, using periodic properties, and evaluating trigonometric functions with a calculator. Okay, up first. So we already discussed the unit circle in our last section. We were looking at angles, and we just said, well, if you go all the way around with an angle of 2 pi radians, you're going to form a circle. Well, that's the case here. So it's all the way around. Now, a unit circle is specifically in which the ray that forms our initial portion of our angle is exactly 1 unit in length. So that's why it's called a unit circle. Now, if I'm talking about a unit circle, then any point on the circle, since I know it's a unit circle, it's going to be a distance of 1 from the center of that circle. And I can say that given the Pythagorean theorem, then x squared plus y squared is going to equal 1, because I can say, well, x, it's just the horizontal distance any point is. The y value is going to be the vertical distance, so I could create any triangle within here that I wanted at a given x value and a given y value, and the hypotenuse would always be 1. Thus, x squared plus y squared is going to be 1. That's going to be the equation of that unit circle in the rectangular coordinate system. Now, in a unit circle, the radian measure of the central angle is equal to the length of the intercepted arc. Both are given with the same real number, t. Now, usually we either call that angle t, or another commonly used angle is theta. It's sometimes alpha, but t and theta are the most common. Now, I went ahead and gave you a unit circle. Most likely, if you've been in a trigonometric class, even maybe the trigonometry as part of an algebra 2 or pre-calculus in high school, you've looked at the unit circle before. If not, or even if you have, please make sure you know this. This unit circle should be committed to memory. So you need to know all of the angles in both radian and degree form. So remember, we can go in increments of pi/6, where you say, well, that's going to be all the angles that split our quadrants into thirds. So we have 1 pi/6, 2 pi/6, 3 pi/6, 4 pi/6, 5 pi/6. This would be 6 pi/6, 7 pi/6, 8 pi/6, 9 pi/6, 10 pi/6, and 11 pi/6. That's the same thing as going in increments of 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, and 330. So we have to know all of those. And then please look at what our values on the unit circle are at that point. Well, at a 30-degree or pi/6 radian angle, you should know that the horizontal component is greater than the vertical. And you could see that easily. If you dropped down a triangle, you could say, well, please look, the base of that triangle almost goes all the way out to 1. Well, the square root of 3/2, if you put that as a decimal, it's 0.866. So you say, yeah, it's about 87% of the full distance we can go out for the horizontal portion. So the x component at an angle of pi/6 is the square root of 3/2. Well, what's the y component? Notice here, guys, if you took this y value back over here to your y-axis, that is precisely half of the distance up from 0 to 1. So you said, well, then it's no surprise that at an angle of pi over 6, the y value is 1/2. What happens at the angle of 2 pi over 6 or pi over 3? Please notice those two coordinates just flip. So you say, so now the x component is exactly 1/2 of the distance. And if you just look at it, you can see, yeah, the x component is half of the distance from 0 to 1 at an angle of pi over 3. And it's the y value that moves up really high. It's the square root of 3 over 2 at this point. And you'd say, yeah, because at pi over 3, the y value, if I drag it back over, it would be almost the full height it could ever take on. And at this point, it's the square root of 3 over 2. The same two relationships occur in each other quadrant. At 2 pi over 3, it's going to have the exact same y value as it does at pi over 3. And we can see why. It has the exact same y value. The x value, it's just the negative since you're moving to the left. At 5 pi over 6, again, our values are going to be the same, except the x component is a negative square root of 3 over 2 since we're moving to the left. At 7 pi over 6, you see, well, it's the same thing as 5 pi over 6, except now the y value is moving down because we're looking at our y-axis and we're below 0, halfway between 0 and -1 at an angle of 7 pi over 6. 4 pi over 3, you should say, well, it's the same two values that you see at pi over 3 and 2 pi over 3, except now the x component and the y component are negative because we're moving to the left and we're moving down. At 5 pi over 3, you said, well, that's the same thing as 4 pi over 3, except our x component is positive since we're moving to the right a half of a unit. And then finally, at 11 pi over 6, you would say, well, 11 pi over 6 and 1 pi over 6 have the exact same two x and y components. Again, with the exception, the sign on that y component's negative since it's moving downward 1/2 of a unit instead of upward 1/2 of a unit. Now, when you look at the mid-quadrantal angles, those angles that split each quadrant in half, that's our 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, and 7 pi over 4. So if you think about it, well, any odd number over 4, it's always going to split a quadrant. At any value that splits a quadrant, the x and y components are both the square root of 2 over 2 every single time. And you say, well, okay, yeah, they're the square root of 2 over 2, but their signs can change. Yeah, sure they can. And it's easy to know how they change. Because at pi over 4, both the x and y component are the positive square root of 2 over 2. Now, if you do the square root of 2 over 2 as a decimal, you'll get 0.707. So what that means is if you dropped this and brought a triangle down here, that x component is approximately 71% of the way from 0 to 1. And you said, well, yeah, it's about 71%. Same thing with the y value. Since it's also the square root of 2 over 2, you'd say it's approximately 71% of the distance from 0 up here to 1. So now we can say, all right, that tells me pi over 4. They're both the square root of 2 over 2 and the square root of 2 over 2. What about 3 pi over 4 that splits quadrant 2? You'd say, well, it's moving to the left, so its x component has to be the negative square root of 2 over 2. What about 5 pi over 4 down here? It's the exact same two values, except both of the x and y components are negative. Since we're moving to the left and we're moving down, they're both the negative square root of 2 over 2. And finally, at 7 pi over 4 units short of a full revolution. Remember, a full revolution, 2 pi, that's the same thing as 8 pi over 4. So you'd say, well, then this is 1 pi over 4 less than that. It's 7 pi over 4. And at this angle, you can say, okay, again, the x and y components still are the square root of 2 over 2, but the y component is moving down, so it's a negative square root of 2 over 2. Now, I have here what's positive and negative in each of these quadrants, but as long as you just keep in mind, hey, the sine is going to be the y component on the unit circle. The cosine is going to be the x component on the unit circle. Then you won't have to memorize any of this stuff, and you can just keep the the sine straight by just knowing cosine is the x component, sine's the y. So without even looking at this, you could just say, oh, well, I know the cosine is going to be negative in quadrant 2 and quadrant 3. Why? Because the x components are negative there. I know that the sine is going to be negative in quadrant 3 and quadrant 4. Why? Because the y value's negative down here. Sine's going to be positive in quadrant 1 and 2. Cosine's going to be positive in quadrant 1 and quadrant 4. Now, up next, our 6 trigonometric functions. We have sine, cosine, tangent, cosecant, secant, and cotangent. I have each of their accepted abbreviations there. Please just remember those abbreviations aren't used unless there's an angle after them. So you would never say the sin is equal to anything. You'd say the sine of theta, the sine of x, the sine of t. So whenever you're using their abbreviations, you always have an angle written after them, such as on this page. So definitions of a trigonometric functions in terms of the unit circle. What I was saying back here on the unit circle, where I said the sine is just the y values, the cosine is the x values, that's what I'm saying right here. The sine of any angle t on the unit circle, it's just the y value on the unit circle. So is it good for you to be thinking, all right, one definition of the sine function is it's the y component on a unit circle? Please, absolutely, yes, that is a definition of the sine function. What about the cosine function? It's the horizontal component on the unit circle. So any x value on the unit circle is the cosine at that angle of t. Now, the tangent is the ratio of sine over cosine. In terms of the unit circle, you just say, well, if you have some value in the unit circle and you wanted to know the tangent, like for example, real quickly, if I said, hey guys, tell me what the tangent of pi over 3 is. You'd say, well, it's just the y value over the x value. If I took the y value over the x value at pi over 3, I'm going to get the square root of 3. I guarantee you the tangent of pi over 3 is the square root of 3. You could go to your calculator. It's going to be 1.732. If you type in tangent pi over 3 and you're in radian mode, it's going to give you 1.732 because that's what the square root of 3 is. Now, if I go to cosecant of t, it's 1 over the y value because it's simply the reciprocal of the sine function. Secant's the reciprocal of cosine, so it's 1 over x. And cotangent is simply the reciprocal of the tangent function, so it's x over y. Now, it is important to keep in mind each of these functions that have a denominator, they do have values where they're undefined. Sine and cosine, they're going to be defined for any angle. But the tangent, since it has that x value in the denominator, we know the tangent's not to exist whenever the tangent will fail to exist whenever the x component is 0. So if I say, hey, what's the tangent of 90 degrees? Or what's the tangent of pi over 2? Does not exist. What's the tangent at 3 pi over 2 or 270? Does not exist because its denominator would be 0. Similarly, the cotangent would be undefined at 0 or at pi radians. So we just have to make sure that their denominators are not 0. And if they are, they're just undefined at those angles. Now, if we're finding angles of trigonometric functions, it says use the figure to find the angles of the trigonometric functions at t. So let's say I tell you that the sine of t, which is the y component on the unit circle, is 1/2. So automatically, whenever the y component is 1/2, we should just know from our unit circle, well, if the y component is 1/2 and the x component is the square root of 3 over 2. Well, what if you didn't remember that from your unit circle? You could go back and use the Pythagorean theorem and say, well, we know that the hypotenuse for a unit circle has to be 1. So then you could say x squared plus 1/2 squared is equal to 1 squared and use that to solve for the horizontal component. But in this case, I'm just hoping you'll have that in mind from the unit circle and say, well, all right, if we're in quadrant 1 and the y value is 1/2, then the x component is the square root of 3 over 2. Well, what's the tangent? It's that y value over the x value, 1 over 2 divided by the square root of 3 over 2. That's going to simplify to just be 1 over the root of 3. Now, I would accept the answer 1 over the root of 3. Typically, your book will always want a rationalized answer. I'm not honestly a fan of rationalization, but we'll do it just because your book wants it done that way. And in order to match the answers on My Math Lab, you may need to. So they would want you to multiply by the root of 3 over the root of 3, which is just going to give you the root of 3 over 3. But again, for me, I'm fine with this answer right here. I kind of like the unrationalized answer, but this is what your book will more often want. Now, for the cosecant, we can say, well, we already know that's just the reciprocal of the sine. If the sine is 1/2, then the cosecant is 2. The secant is nothing more than the reciprocal of the cosine, so I know, well, then the secant's going to be 2 over the root of 3. Please notice that's what I did here, 2 over the root of 3, and then I can say, well, that I'd have to rationalize by multiplying by the root of 3 over the root of 3 to get 2 on the root of 3 over 3. And then I can say for the cotangent, it's just the reciprocal of the tangent. I knew that the tangent was 1 over the root of 3. So the cotangent has to be the root of 3 over 1, which is what I get, the root of 3 there. Now, for domain and range of the sine and cosine function, the domain of both functions is -infinity to infinity. That's because you can plug any angle into them. You can revolve as many times around the unit circle and get any angle you want, both positive or negative, and it's always going to have a sine and cosine value. But because the sine is representing the y value, you can say, well, then the lowest the sine could ever be is like, for example, at an angle of 3 pi over 2. The sine is -1 there. The greatest the sine could ever be is at an angle of pi over 2, which it's 1 at that point, and it does include those values. And similarly for the cosine function, its greatest y value is at 0, which is 1, and its smallest y value is -1, and that occurs at an angle of pi. So you can say, well, both of them have a range of -1 to 1, and that endpoints are inclusive or are included. That's why you see brackets. Now, at trigonometric functions that split the quadrants, so go in increments of pi over 4, occur frequently. So we need to be comfortable with those. And anything at pi over 4, you automatically should know, well, the sine and cosine have the exact same absolute value. They're going to be the square root of 2 over 2 each one. Where that comes from is, again, your unit circle definition. If you know that it splits a quadrant, then the x and the y value, the a and the b in this example here I have, would be the exact same thing. So instead of saying a squared plus b squared is c squared, you can just say, well, it's a squared plus a squared, because you're going over and you're going up the exact same amount. So you might as well say 2a squared. Well, then that gives me a squared is equal to 1/2. And then since I know it's moving to the right, it's not positive or negative. If I'm in quadrant 1, it's positive. And I can say, well, it's positive square root of 1 over 2. Which when I rationalize, that's the same thing as 1 over the root of 2. We rationalize by multiplying by the root of 2 over the root of 2, and you get the root of 2 over 2. So then you can say, well, yes, both the x and y component are the square root of 2 over 2 there. And you can also see why at 3 pi over 4, the x component is going to be the negative square root of 2 over 2, because it's moving to the left. So here where you're taking the square root of both sides and you say, well, it could have been the positive or negative. It's just going to depend upon the quadrant as to whether you're choosing that positive or negative. If we're talking about the angle pi over 4 in quadrant 1, both the x and y components are positive there. So now, if I look at finding, for example, any other values at pi over 4 here, if I say, well, the cosecant, we've already said that we know that the sine is the square root of 2 over 2. So the cosecant would be the reciprocal of the square root of 2 over 2, or which is just 2 over the root of 2. Now, you could think of it as, well, 2 is the same thing as the root of 2 times the root of 2. If I have that divided by the root of 2, clearly my answer is the root of 2. You could also rationalize by multiplying the numerator and denominator by the root of 2, but then that requires you to do the additional step of canceling out your 2 to get to the root of 2. I would rather you just look at this and say, well, 2 divided by the root of 2 is the root of 2, because you've got 2 factors of the root of 2 in that numerator. Similarly for the secant, of course, since the cosine's the same thing, the reciprocal of the cosine's going to be the same, and you'll still get your square root of 2 there. For the cotangent, well, please notice your tangent and cotangent are both 1 here, because you just say, well, since the x and the y values, the sine and the cosine, they're both the square root of 2 over 2. So it doesn't matter whether you do x over y or y over x, it's a 1, since your numerator and denominator is the same. So we can get all of our angles at pi over 4. As we've discussed, the sine and cosine are both the square root of 2 over 2. The reciprocals are just the root of 2. And then the tangent and the cotangent, which is saying the sine over the cosine or the cosine over the sine, it's just 1, since those values are the same. Now, when we talk about even and odd functions, please remember, even functions are functions that are symmetric with respect to the y-axis, and you can say f of negative x is equal to f of x. You can think of it as just y equals x squared. And you say, well, yeah, it's an even function because I can plug in a 2 and get f of 2 is 4, and a negative 2 and also get f of negative 2 is 4. So you can plug in negative values and get the same thing. If you go back, and let me do this real quickly, because I want you to understand this based on the unit circle. If you go back to this, you can see that the cosine function is an even function. How can you see it? Please notice, this is pi over 6. What's the cosine at pi over 6? It's the square root of 3 over 2. Well, what if I told you to rotate a negative pi over 6? You'd say, well, negative pi over 6 would have me rotate this way. Well, f of pi over 6 for the cosine function, square root of 3 over 2. The cosine at negative pi, still the square root of 3 over 2. What about the cosine pi over 4, square root of 2 over 2? What's the cosine of negative pi over 4? Still the square root of 2 over 2. What if I said the cosine of 2 pi over 3? Way over here, you'd say, well, the cosine at 2 pi over 3 is negative 1/2. What if I ask you to find the cosine of negative 2 pi over 3? You'd say, well, if I rotate 2 pi over 3 radians in the negative direction, it's just going to take you to 4 pi over 3. You see, cosine's the exact same value. So what I'm wanting you to see is you can change the sign of the angle inside the cosine function and you get the exact same thing. Cosine is an even function. Now what about the sine? The sine is going to be an odd function. Please notice why, and it's very quick to see why. If I change the sign of the angle inside the sine function, like here's sine pi over 6, it's 1/2. What's the sine of negative pi over 6? Well, the sine of negative pi over 6, negative 1 over 2. So f of negative x is equal to the negative of f of x. So same thing happens at pi over 4. Sine of pi over 4, square root of 2 over 2. What's the sine of negative pi over 4? It's the negative square root of 2 over 2. So all I'm saying on this page when I'm talking about the even and odd functions is what you should be able to see just by looking at the unit circle. The cosine is an even function because you can change the sign on the angle and it's the exact same thing. Now, since the secant's the reciprocal of the cosine, it's the same thing with it. If cosine's an even function, then its reciprocal is an even function. The sine function is an odd function, so its reciprocal is also odd. It turns out that the tangent function and the cotangent function are also odd functions. If you change the sign of the angle within, then it's going to change the answer. And you can see that like if I say tangent of pi over 4 and tangent of negative pi over 4, the tangent of pi over 4 is 1. The tangent of negative pi over 4 is negative 1 because your sine and cosine have opposite values there. So, for example, here, I'm asking you to evaluate the secant at negative pi over 4, and you'd say, well, we've already evaluated the secant at pi over 4 and found it to be the square root of 2. What we know from this previous page is that the secant of negative pi over 4 is going to be the same thing as the secant of pi over 4. So it's also the square root of 2 over, just the square root of 2. When I look at my sine function, the sine of negative pi over 4, I know since the sine function is odd, it's going to be the negative of the sine at pi over 4. Because instead of moving the y value up, it's now going to be moving the y value down. You just say, well, it's the negative square root of 2 over 2. Now, fundamental identities, you need to know that the sine is, or that the cosecant's the reciprocal of the sine, the secant's the reciprocal of the cosine, cotangent's reciprocal of the tangent, and vice versa. You can say, well, the sine's the reciprocal of the cosecant, the cosine's the reciprocal of the tangent, and the tangent's the reciprocal of the cotangent. So all of those reciprocal identities, and that the tangent is equal to, we said on the unit circle, it's y over x. Well, it is. It's also sine over cosine. And it's the same thing as saying the y component over the x component on the unit circle, since the sine is the y component in the unit circle. The cosine is the horizontal or x component on the unit circle. The cotangent's just the reciprocal of that, so it's cosine over sine. Now, looking at another example here, if I say, hey, let's give you that the sine of t is 2/3, and that I know that the cosine of t is the square root of 5 over 3. Find the value for the 4 remaining trigonometric functions. Well, what I know, since both the sine and cosine are positive, this has to be in quadrant 1. Now, I also know that the tangent is just the ratio of the sine over the cosine, so I could take the sine value here, divide it by the cosine value, and that's just going to simplify down to be 2 over the root of 5, which then I rationalize and call 2 on the root of 5 over 5. For the cosecant, you can just say, well, it's just the reciprocal of the sine, so it's going to be 3 over 2 here. For the secant, it's the reciprocal of the cosine, which you get 3 over the root of 5, and then rationalize that and call it 3 on the root of 5 over 5. For the cotangent, we know that that's just the ratio of cosine over sine. So you'd say, well, cosine over sine, or I have 1 over tangent there. I could just look at this up here and say cosine over sine. Well, that would be the root of 5 over 2. And then the root of 5 over 2 needs to be rationalized. And you could say, well, the root of 5 over, no, actually, it's easier just to look up here. The root of 5 over 2 is already rationalized. So instead of doing 1 over tangent like I did here, which is okay, you can do 1 over tangent. So you can take this answer, take the reciprocal of it like I did here, or you could just look at it and say, why not say the cotangent's the cosine over the sine, and you can see it's going to give you the square root of 5 over 2, which is your final answer there. It just depends how you wanted to do it at the time. In this case, I think just saying cosine over sine is quicker. Now, the Pythagorean identities, please remember, we said that the sine is just the sine is the vertical component. It's the y value on the unit circle, and the cosine is the x component, the horizontal component on the unit circle. Since that's the case, you could draw a triangle to any point on the unit circle, your x component, y component, up to the point on the unit circle, and then draw it down. Your radial length to the circle is 1. Because of the Pythagorean identity, you can just say, well, hey, a squared plus b squared is equal to c squared, which in this case, c squared is always 1. Well, that can be written as sine squared plus cosine squared is 1 now. And again, that's just because that's the vertical portion squared on your triangle. This is the horizontal portion squared on your triangle. And this is your radius squared. And the radius is guaranteed to always be 1. Now, because of those reciprocal identities, we could say, well, all right, what if we went through and took this entire equation and divided by a cosine? And the cosine squared over cosine squared would be 1. Sine squared over cosine squared would be tangent squared. 1 over cosine squared would be secant squared. What if I took this entire equation and divided by a sine squared? Sine squared divided by sine squared is 1. Cosine squared divided by sine squared would be cotangent squared. And 1 divided by sine squared is cosecant squared there. So these are just 2 additional Pythagorean identities that are just a direct result of that first one. This second one is the first one divided by cosine squared in every term. The third one is the first one divided by sine squared in every term. Now, using that for some identities. If I tell you that the sine of t is 1/2, and that t is between 0 and pi over 2, so we're in quadrant 1. And then I'm wanting to find the value of the cosine of t. So you say, well, No problem. Sine squared plus cosine squared has to be equal to 1. And then you could say 1/2 squared plus cosine squared is 1. We'll get 1/4 plus cosine squared is 1, which gives me cosine squared is equal to 1 minus 1/4. Cosine squared would be 3/4. So now you know whenever you take the square root of both sides, usually you'd have to say, well, the side not containing the variable needs to be plus or minus the root. Not in this case, because we know it's moving to the right, so it's only positive. So you say, well, it's the positive square root of 3 over 4, which gives me my square root of 3 over 2, which hopefully you already knew based upon our unit circle. You say, well, of course, the horizontal component is the square root of 3 over 2 when the y component is 1/2 in quadrant 1. That's at the angle of pi over 6. Now, periodic properties. Because these angles between 0 and 360 or 0 and 2 pi, they merely just keep on repeating and repeating and repeating. Our sine and cosine functions repeat their graphs. Excuse me. And I can say the angle sine of t plus 2 pi is always going to equal the sine of pi. This is showing me that the sine function has a period of 2 pi radians. Whether I'm talking about the sine of 0, the sine of 2 pi, the sine of 4 pi, the sine of 6 pi, I can keep on adding 2 pi as many times as I want. It's going to keep on going back to the sine of 0, which is 0. Similarly, if I say, well, what about at an angle of 0, the cosine of 0 is 1. What's the cosine of 2 pi? It's also 1. What's the cosine of 4 pi? Cosine of 6 pi? Cosine of 8 pi? It's all 1. Every time you add any 2 pi, it goes back to the exact same point on the unit circle. So we can say the sine and cosine functions are periodic functions that have a period of 2 pi. Now, the tangent and cotangent, they actually have a period cut in half of that, and they're going to repeat their values every pi radian. So the tangent and cotangent have a period of pi. So, for example, here, if I say, well, the cotangent of 5 pi over 4, we'd already been talking about the cotangent of pi over 4 previously, which is why I'm using this. Cotangent of pi over 4, we said, was 1. Now, whether you use this or just your knowledge of the unit circle, I want you to know that the cotangent of 5 pi over 4 is also 1. When I'm thinking of it, I'm thinking of 5 pi over 4. Well, that's the angle that splits quadrant 3. At that point, the sine and the cosine are both the negative square root of 2 over 2. So, of course, the ratio of the cosine over the sine is 1 there. But what your book would like you to think of is, well, since every pi units, the cotangent function repeats its values, whatever the cotangent at pi over 4 is, it's the exact same thing as the cotangent at 5 pi over 4. They're both 1. If I did the cosine of negative 9 pi over 4, so I could think of that and say, well, a cosine of negative 9 pi over 4, that would be a rotation all the way around to negative 8 pi over 4, and then negative 9 pi over 4 would rotate another pi over 4. It would split quadrant 4. Now, it would be coterminal to an angle of 7 pi over 4 in the first revolution, and I know that the cosine there is going to be the square root of 2 over 2. Another way to think about that, though, is since the cosine function repeats every 2 pi radians, I could just say I could take my negative 9 pi over 4, and the first thing I'm doing here is I'm using the fact that the cosine function is even. I can say, well, the cosine of negative 9 pi over 4 is the exact same thing as the cosine of positive 9 pi over 4. And then what do I know about the cosine of 9 pi over 4? It's equivalent to the cosine of pi over 4 plus 2 pi. And then since the cosine function repeats itself every 2 pi radians, you can just say, well, then it's the exact same thing as the cosine of pi over 4, which is the root of 2 over 2. Pretty cool stuff. Now, repetitive behavior, this is what I was talking about. The sine function has a period of 2 pi radians. So every 2 pi radians, it's going to repeat itself. Same thing for the cosine function. The tangent function repeats itself every pi radians, as does the cotangent function. To evaluate trig functions, we'll use the keys on the calculator marked sine, cosine, and tangent. Remember, it's our abbreviations, SIN, COS, and TAN. Be sure to set the mode. And now this is critical. Most often when students miss problems that are calculator oriented, it's because they're in degree mode when they're supposed to be in radian mode, or in radian mode when you're supposed to be in degree mode. Just make sure you understand what you're supposed to be in on any particular problem, and it should be extremely obvious. Degrees, you have to see the degree sign within the sine, cosine, or tangent function to be in degree mode. Otherwise, if you don't see a degree sign, you're supposed to imply that it's in radians, whether it explicitly says radians or not. Now, for example here, I have the sine of pi over 4. Well, you should be in radian mode for this one. We know that the sine of pi over 4, we've already been talking about, it's the square root of 2 over 2. On your calculator, that'll give you approximately 0.7071. If you did the cosecant of 1.5. Now, this is one where a student might think, oh, am I supposed to be in degree mode? I don't see the pi's. You should not be in degree mode here. In order for degree, you would actually have to see the degree sign. This is meant to be the cosecant of 1.5 radians. So since the cosecant's not a function on the calculator, you would need to rewrite it as 1 over the sine of 1.5. You should be able to go into your calculator at that point and just say, well, 1 divided by the sine of 1.5 is going to be approximately 1.0025. And let's see. Oh, we've reached the end. Oh, I'm sad. I was thinking that there was more to it. So that is the end of this 4.2 lesson. Please do check with my solutions online for the problems I worked out of the book. I had fun doing the problems out of the book in this section. And if you struggle with anything on my math lab as you're trying to do it, please let me know. I'm happy to help in any way I can.